Alright, so in this lesson we're going to start talking about refraction and how refraction works, and then get into a little bit about lenses. In the next couple of lessons we'll look at lenses in a lot more detail. So the first thing to point out is that when light travels through a vacuum, it travels at a speed of about 3 times 10 to the 8th meters per second. Light can also travel through many other materials, and in fact, since light is electromagnetic radiation, if we were to expand it beyond visible light, other forms of electromagnetic radiation can travel through materials that visible light cannot. When light enters solids and liquids, it tends to slow down quite a bit. The atoms of that material, in order for the light to transfer that material, need to absorb and re-emit that light, and so that ends up changing the speed at which light can travel through a material that's a solid or a liquid. And that change in speed is really dependent on lots of factors within the material. So one way that we use to define this change in speed is to define what's called the index of refraction, and we use n to talk about the index of refraction. And what the index of refraction is it's the ratio of the speed of light in a vacuum to the speed of light in that material. So here's some indices of refraction for some common substances. What you'll notice is that some liquids like water, 1.3, ethyl alcohol would look fairly similar to water, 1.362. If we looked at some solids, sodium chloride, ice, diamond. If we look at something like air and a lot of these gases, they're pretty close to 1. What that means is that the index of refraction of a gas is pretty close to 1, meaning the speed at which light travels through that gas is basically the same as the speed at which light travels through a vacuum. Now, what happens when light interacts with another medium? So say going from air into water. So what's going to happen is you have this incident ray, so you have this ray moving down into the light. Well, what's actually true about this ray is that you have all these little wave fronts. You can think of these like the crests of the light rays. Well, when it interacts with this medium, those wave crests start to slow down. What ends up happening to the ray is that something that was traveling in this direction before it interacts with the material now travels this direction. The direction that this light travels changes. And we can actually relate the angle here and the angle here to the indices of refractions of the two mediums. And this is what's called Snell's law. And what it says is if I know the index of refraction of medium 1, n1, and I know the incident angle of medium 1, what I'm going to call theta 1, and I know n2, the index of refraction of medium 2, I could calculate the refracted angle. And so what this says is n1 sine of incident angle equals n2 sine of refracted angle. Now you can actually go through and play around with the right triangle trigonometry and prove to yourself that that is true. It happens to work out there are two similar right triangles where these opposite sides are related to the indices of refraction. So let's do a quick sample problem. Let's say we have light that strikes the surface of a swimming pool at an angle of 46 degrees with respect to the normal. Now it's worth pointing out that we measure the angle of incidence and the angle of refraction with respect to the normal as well. The index of refraction of water is 1.33. We can assume the index of refraction of air is pretty close to 1. What we want to do is determine the index of refraction if the light ray is going from the air into the water or the light ray is going from the water into the air. So there's two ways this light ray could strike this surface. One is going from the air into the water, the other is going from the water into the air. So each way we're going to use Snell's law, and we know the incident angle is going to be 46 degrees. So the only change between these two situations is in the first situation, n1 is 1 and n2 is 1.33. In the second situation, n1 is 1.33 and n2 is 1. So we work this out. This equation will actually be true for both situations. n1 sine of theta 1 over n2 equals sine of theta 2. We could get rid of the sine by doing inverse sine to both sides, which means the inverse sine of 1 times sine of 46 over 1.33 is theta 2, and you get theta 2 is 33 degrees. So this is going from air into water. The light ray gets refracted toward the normal. If we do the reverse, you find that the light ray gets refracted away from the normal. So if you're going from lower index of refraction to higher index of refraction, the light ray is going to be bent toward 90 degrees to that surface. If you're going from lower index of refraction to higher index of refraction to lower index of refraction, it's going to get bent away from that normal. So another interesting thing is, let's say we have a searchlight here and it's being used at night to find the sunken treasure chest. and it wants to know what is the angle of incidence the light should be pointed at to illuminate the chest. So the first thing I need to do is figure out what theta 2 is, and so I can use tangent to do that, and well, I already did that math there. So I know n1, n2. I know what n2 and n1 are for this situation, so we could actually solve for theta 1. We've got water and air, and so theta 1 has to be 44 degrees. It's worth pointing out this is really like part B of the last sample problem. Solve for one of the angles. Now the other interesting thing about this is if you were looking at this from the boat, there's a virtual image of this object that's going to appear at a different depth than the actual object. If you're looking at it in this direction here, and you know how far this direction is, what it's going to look like is that this line is actually pointed in this direction. So your image will, or your eyes will actually interpret light as traveling in a straight line, not bent by the water. So while your light eye will be able to see this distance accurately, it sees this distance in this direction. And so the chest will not appear as deep as what it actually is. You can actually calculate what apparent depth is by knowing the actual depth of an object and then the indices of refraction of both the surface or the air and the liquid. The second thing we want to talk about is total internal reflection. If you're going from a higher index of refraction to a lower index of reflection, there are two things that kind of happen that are cool. First thing is that when this light ray strikes the surface, some of the light gets reflected away from that surface. This almost acts like a mirror. If you've ever been underwater and looked up, you'll notice that some of the light is getting reflected back into the water. And some of it gets refracted, and it gets refracted away from the normal. Now if we start to bend this, this would also bend this light ray further and further down, and we could get to a point where that refracted light ray refracts along the surface of the liquid, or theta 2 is 90 degrees. We call this the critical angle. What happens beyond the critical angle is that we get total internal reflection. All of this light ray gets reflected into it. It's also worth pointing out that the bigger this angle becomes, the more and more light gets reflected and the less light that gets refracted. So if we wanted to figure out the critical angle, all we would really need to know is n2 and n1. It's worth pointing out this only happens if you're going from a medium of higher index of refraction to a medium of lower index of refraction. So let's get an example problem. And so let's say we have this figure on the right which shows an optical fiber that's going to consist of a core made of flint glass, and it tells us what the index of refraction of flint glass is, and it's surrounded by a cladding made of crown glass, and it gives us its index of refraction. And it says a ray of light is going to enter the cable at an angle theta 1 with respect to the normal. And what we want to know is what is this angle so that this light ray will strike the cladding just above the critical angle, meaning the total internal reflection will happen inside this optical fiber. Basically how an optical fiber works is you shine a beam of light through here and the beam of light reflects. Total internal reflects inside this core, and that's what actually carries the information for you. So there's the known pieces of information, and there's the three unknown pieces of information. I don't know the critical angle, I don't know theta 2, I don't know theta 1. It looks like I could find theta 2 if I knew the critical angle, because these two look like they have to be related to one another. And sure enough, it looks like theta 1 plus critical angle should be 90 degrees, because this is a right triangle and that angle is 90 degrees. Looks like I could relate these two angles together using Snell's law, and looks like I could find the critical angle by using the critical angle formula. So, excuse me, in my previous slide, sorry, what I had confused is this should actually be N flint glass, not N crown glass, and I changed it on this slide. So let's do some algebra. We can actually calculate out what the critical angle is. It's 66 degrees. What that means is the angle of refraction here would have to be 24 degrees. What that means, if we work that out, is that the incident angle has to be 42.7 degrees. So I've really done three things. I calculated the critical angle, I used this relationship to calculate the refracted angle, then plugged it in and used this relationship to find the incident angle. So that kind of does a quick overview of refraction and Snell's law. We'll start to look at in the next few lessons is how lenses work.